Dear Sam
Dear
Presto,
student, my name is
thanks
Subhrodip
for
and I am your
connecting to me.
tutor on homeworkmarket.com. Thanks for working with me. So first, you was telling me that the Excel file wasn't working. Let me show you how the macro can work, how to enable it to work so that it works. So first of all, the default setting of macro is that macros shouldn't macros and ActiveX control shouldn't work on the computer by default. They should need to be enabled, and this is because data can be easily stolen by a piece of code. So the settings that I'll show you how to set up, will actually let you see a kind of a yellow bar that you can see right now on the screen. Do you see the yellow bar? Right. So first is the enable editing, and then you will see a security warning. The security warning I was talking about. You can see the security warning, and it says macros have been disabled. So I can click on the enabled content, but before that, this warning must show. This warning must show every time you open an .xlsm file, so that you can choose whether to enable it or to not, depending on the level of trust you share with the owner. And then go to files. This is the security warning, but it should show. So how do I make it show? Right. So here is the options. You'll see when you click on file, you'll see options. Options, and I click on options, and then I see there is a trust center. And on the trust center, when I click the trust center, I'll see something called trust center settings. Can you see it? Right. Trust center files, options, trust center settings, and I click on trust center settings. First thing is the message bar that shows. Suppose you are here, you don't click any of these things, you just see the macro settings. And the macro settings, this is potentially dangerous. If you enable all macros, don't do it. Disable all macros without notification, it's bad. The same kind of problem will persist. Disable all macros with notification. The notification will be the yellow bar, white visible, and then you will choose if or not to enable the macro. Disable all macros with notification is the setting, and then there should be a message bar which enables this message. Show message bar in all applications when active content such as macros have been blocked. This must be set on. So this on the message bar and the macro settings. Both of these are on. Good. Okay. And then you click the enable content. That's it. And you see there's a macro out here which is at every time. So you can also see that pressing the Alt and F11 content opens the VBA editor from where you can see what's the code in it. So for example, this was for the to calculate some kind of a binomial here. So that's it. Name conventions. So now we are going to cover name conventions. What is capital XI? Well, capital XI is a random variable. So let's say that we have a black box, and inside the box there are different colored balls. Now I am going to pick up a ball at random, and I put my hand into the jar. I have picked up a ball. Now that ball is a random variable. Why is it a random variable? Sorry, the ball is not a random variable, its color is a random. Why is it random? Because it can be anything. It can assume any value. So that's why it's a random variable. So you were confused within the small xi and the capital Xi. Actually, I could have made it, you can see this is the book1.xls and this is the sheet which accompanies your discrete probability distribution problem, the Poisson one. And there is both this capital X and the small x, the capital X size and a small x size. My purpose of choosing this sheet is precisely this, so that I can explain you what are these small x size and what are these capital X size. This is just a naming convention. This could be a small si, where s would have denoted the state. But then in our case, this can be a set of finite states, because beyond a certain state the probability will be closed down to 0. This is a finite state because after a certain stage the probability will be coming down to 0. As you can see that in the 13th count, let me show you, it's almost down to 0, and the probability that xi is greater than or equal to 13, yeah, it's 0.0000 and then 5, 9 or whatever. So that's why we could have done it an SI, but in most places we do it's a small xi is a naming convention, because xi could be continuous as well. For example, let's see the other sheet, right? Yeah. So it can assume value of 37.17, 578, 37.13577, and both of these are distinct values. On the other hand, here we have only values of 0, 1, 2, 3, 4. It can take up integers valued. Right. So that's why we have the probability. This is correction, right? I had given equal to xi, but if you see the formula, it's corrected in the what's this? Yeah, it's corrected in the sheet, I believe so. This is the theoretical probability distribution, and you can see it's corrected. It's the theoretical probability. In 13 you see the number is small, it's not what we have right here. We have quite a high number out here, which is a cumulative probability distribution. So when we add this is the cumulative probability distribution at capital Xi is less than equal to 12, or at capital Xy equal to 12, the CDF will be, the CDF stands for probability that it's less than or equal to 12. It is less than or equal to any value xi, right? That's the CDF. This is the CDF, and this is the PDF. So when we add this value to this, we get this. Okay, so now we have our case. What's the k of xi? It's the cumulative, it's a function of the cumulative probability. So we have just taken it to an integer value. And then what have we done? We are drawing random UIs. We are drawing random case based on these UIs. And then we have, say, 6856 as a ki. So since this is a binning, or these values are cumulative values of ki, so I look for the 6856 here. No, 6856 isn't here. We have 6483, but that's a k for, that's the max k for xi. small xi. So if capital Xi has to be 4, then the value has to be less than 6483 and 4532. But that's not the case. It's greater than 6483. We have 8005 as the next value, so lies in somewhere here. So it's 5. Because it's certainly greater than this, so it can't be this. It will be 5. That's how the k have been binned. These are the cumulative probabilities or the max. So when it crosses max, it gets here and so on. Just a convention. And then to illustrate the concept of capital Xi better, let me do this. So when n is 1, we have got a k of, or 0, we have got a k of 7056. That corresponds to, let's search 70, yeah, 5. So n1 equals to 5. I draw it again. It's 5553. This is n2. This is, what is this? 5553, 5553 comes n4. Then x1 is again 4. Now, sorry, x2 is 4. x2 is 4 because this is the second row, right? So we could have filled up the table in this way. This is the way standard Excel would have filled it up. But now I want to enter one n, and at the click of the button, all the draws should be generated. So what I do is here, 1000 or say 100. So I click the button draw, and you can see n0. So the convention is actually to make it n1 to, so you'll have 1 added, so this would be n100 and this would be n1. But you can of course define the I in your way, because it's a counting system. It's not necessary to put it at 1, but yeah, that's a convention we follow. And then you can see how the keys have been generated. In this problem, we didn't explicitly need to bin it against it, therefore we needed to generate the PDF, so we had to bin it. We have binned it and generated our PDF. But well, again, that was not a necessary, so we didn't show our realized Xi's every time, capital Xi's every time. But however, yeah, I've saved it, that's a small caveat. We have got our Xi's here, see the probabilities. We have got our probabilities, and that has been precisely with the binning. So let me show you the, so you can see, right, it's a Poisson. This is a way of defining a random variable's distribution. This is the distributional definition. And then I write what is the random variable. It's the number of deaths in a year, such that, this is the symbol of such that whole numbers. It can be 0, it can be 1, it can be 2. Xi belongs to this set. And then this should look familiar. This is the PDF of a Poisson distribution. This is the PDF of a Poisson distribution. And then we have used the term CDF here, cumulative, and therefore we did not show you that Xi is less than or equal to. But then yeah, I've shown you on the Excel sheet this time. This is the CDF, the summation, less than or equal to, and this is the PDF, the probability. So when we add 3, the probability at 0, 1, 2, 3 and 4, we get to a point somewhere here, the 80%. And you can always do a cross check. Again, we have the theoretical probability distribution. You see that the numbers are quite low, which shows that we have on the theoretical probability distribution, and on the cumulative frequency distribution you see how the numbers add up. So it's 0.2042, but the next number is actually this plus this one. Right. Now proceeding to the chi-square tests. So the formula of the chi-square tests has to be explored. It's a very good idea to do that. This is the formula. When you see on the sheet chi squared, you'll see the formula. It's O minus E whole square by E, where E is the observed, E is the expected frequency or the theoretical frequency. O is the observed frequency. So these are the xi's, small xi's, or you could have even written the si's for the state, but we are on the normal distribution sheet, and therefore we have to use a small xi's. So okay, so how does this 2 come here from? Well, less than or equal to 2, because we are leaving many such cases which are less than 26.8. Look at sheet, the exercise number 2. We were discussing about a bell-shaped normal curve, right? So how does a normal distribution look like? Just let me put it on hold. So this is your second. Wow, we can see a normal bell-shaped curve, but we can also, this is the theoretical one, but we also know that this goes beyond this, right? This has a small tail, it's almost 0, but even these numbers are probable numbers on to the left of 26.8 and numbers to the right of 44.8. So the tails of the normal distribution are asymptotics. They never touch the x-axis, so as to speak. That's how we have computed the starting E less than or equal to, and then this was a sensible place to hit the bin, and this was the CDF at 42.8, and therefore the formula is 1 minus the respective CDF cell location in this actual frequency mat, and then yeah, we have got it. So yeah, so a good way of when you get stuck is like your control set, everything is okay. And then we have these observed ones similarly. So I remember editing this one so as to capture it, or it started here and this one was added up. Sorry, it's done in the same version. 1 minus that. 1 minus the CDF at 17 units. And then we had this E, we have this O, and then we can have these numbers. And then when we sum up, we come at the chi-square. When we look at the critical value of the chi-squared, we get the critical value. Since this is less than this, we can conclude that a null hypothesis. All this is a null hypothesis cannot be rejected. If this was greater than 26, then we had to reject the null hypothesis, and we had to say that, well, the substance taught in class did not work here. Now going back to the exercise again, right? In this normal distribution table, however, we have worked out the exercise for exposition, and also that this could be done in no time without wasting time on computational constraints. So this is the magic box. Don't delete this, because this value will get recalculated in the code every time, and we'll have our exercise. Since we are on a continuous normal distribution, the small xi's are any value from 0 to infinity. If I show you the way we have written it down mathematically, real numbers, infinity, and this open interval intersects with real numbers gives us xi. In the Poisson distribution we have written whole numbers. We could have also done this in intersection, well, w or z 0 to infinity. We could have written r subscript 0 to infinity. There are various ways of doing this. Each way is correct. This is the CDF definition of the normal distribution, and you'll note the less than or equal to small xi. Given any value, I can compute the CDF of this random variate, the variable which we don't know. Once we realize it, it's no more random, it's a known, it's a realization, it's no more random. So once we realize xi, it's no more random. So we are talking about probability once we don't know it. Once we know it, it's a certain event. It's not even certain, it's a realization. A certain event is something which has a probability 1, and yeah, of course it's similar to the certain event because we know it. If the color of the ball is not changing and it's black, then 3 hours from now it's going to be black. So that was actually to help understand the concept of capital Xi, and this is the value. So if we had balls and we had numbers on them, then we can talk about an unknown ball when my hand is in the box and I'm holding a ball actually, but I don't know its number. We can talk about something like this. We can talk about xi is less than or equal to small xi. This is the CDF, and then we have it, the mathematical formula of the CDF, and then we have defined success, we have defined failures. Note, since this is a greater range than this, the convention is to do it from 0 to 8362 and then add whatever is left to 8362, and incidentally this is 10,000 because both of these will add up to 1. This happens to be 10,000. This will always be 10,000, or whatever the number of digits, 1 2 3 4, these will be zeros and there will be a 1 on the left of it. So we have got the S digit assignment and the F digit assignment, and then we will generate our UIs. Uniformly we'll get our KIs, and then we will assign these cumulative KIs to an XI. We can also, that's what we have done, but since we had a normal inverse function coming handy which does precisely that, having assigned a KI you get a XI, we use the inverse normal functionality. Even if this was not present, do a Google lookup and you'll find the formula for the inverse normal distribution, which you can always plug in. This was of course faster. So yeah, see the way we have given x is greater than or equal to, this could be xi, y greater than or equal to. What are we trying to calculate? We are trying to calculate the probability of a success, that it's greater than or equal to 37.8. Now you have the piece of code here. I'll encourage you to go and look over it once and ask me. It's good to learn coding in VBA. This is our text box, which is we were clicking. This part of the additional question is this part is shows us how to calculate the difference of means, hypothesis testing for difference in means when we have a realized distribution, or sorry, realized xi, and we want to know if the mu of these xi's, the mean of these random variables, follow a certain distribution, and we want to know whether this xi can come. We are not bothered about the mean of this xi, but we want to know if this xi can come from a mean of our known distribution. So then we calculate the z value and we find the extreme value, the p value corresponding to z. So since it's 0.3, we know that, let's go. My name is Subhrodip Sengupta, and you can Google to find me and get in touch with me anytime as you wish. Thank you again for being with me.